Welcome students. So let's continue with our NCERT chapter 9 which is amines. And today is the theory part 4 and today we are going to cover section 9.6. This is disclaimer. So what is the objective of today's lecture? After attending this lecture, you will be able to understand the topics which we are going to cover today. So today we are going to specifically differentiate chemical reactions, okay? And we are going to distinguish between primary, secondary and tertiary amines. Now for your reference, I have mapped the NCERT sections which we are going to cover today. So today we will be covering 9.6 which is chemical reactions. For your better understanding of the concept, we are going to solve an example which is 9.4. Okay, so let's start with today's lecture. Chemical reactions of amines. So let us start by considering that what influences how amines react. So the reactivity of amines, it depends on several factors, okay? And understanding these factors, they will help you predict how they behave in different situations. First, notice the electronegativity difference between the nitrogen atom and the hydrogen atom in an amine, okay? So I hope you all know what is electronegativity. It is a measure of how strongly an atom attracts electrons. So we know this thing that nitrogen is more electronegative than hydrogen, which means the electrons in the NH bond, they are pulled closer to nitrogen. So this affects the molecule's polarity. The key point is that nitrogen and amines, they have an unshared pair of electrons, which is also called as lone pair. So this make amines nucleophilic. Okay, nucleophilic means they can donate the electron pair to other atoms or molecules. Now let us see how different types of amines like primary, secondary and tertiary, they show different reactivity. So first reaction which we are going to see is the basic character of amines. Now what happens in this? Amines, they can accept proton, that is H plus ions, because of the lone pair on nitrogen, which make them bases. So if I give you an example, you can think of when ammonia, which is NH3, it reacts with hydrochloric acid, which is HCl. So it forms ammonium chloride, which is NH4Cl, okay? Next reaction which we are going to study is alkylation. So what happens in this reaction? An alkyl group, it is added to amine, usually by reacting it with an alkyl halide. As a result, what happens? This increases the size of molecule and can change its physical and chemical properties. So, if I give you an example, then when methylamine, it can react with methyl iodide, which is an alkyl halide, and it forms dimethylamine. Okay? Next, which we are going to study is acylation. So, here what we do, we introduce an acyl group. What is an acyl group? It is CH3C double bond O. So, we introduce an acyl group to amine, often using acyl chlorides. Next reaction is carbyl amine reaction. So it is a specific test for primary amines. So when a primary amine reacts with chloroform and alcoholic potassium hydroxide, it produces an isocyanate, okay, and which has a very, you can say, a strong and unpleasant smell. Next, we are going to see reaction with nitrous acid. So amines also react with nitrous acid. Now here the outcome depends on what kind of amine you have. Okay, you have a primary amine, you have a secondary amine, or you have a tertiary amine. For example, primary aliphatic amines, they react to form nitrogen gas and alcohols, whereas aromatic primary amines, they form diazonium salts. Next, we are going to see aryl sulfonyl chloride, which is known as Heisenberg's test. So this test also helps distinguish between primary, secondary and tertiary amines based on their different reactions with reagent. And last, we are going to see electrophilic substitution reactions, especially for aromatic amines like anilines. So students, one by one, we are going to see all of these reactions, okay, in detail. So we are starting with basic character of amines. Now, if you notice, then there is one interesting thing that amines can act as both. It can act as Lewis base also, and it can act as Bronsted-Lowry base also. Now you must know what is a Lewis base and a Bronsted-Lowry base. So this means it can either donate an electron pair or it can either accept a proton. So if I say it behave as a Lewis base, so what is a Lewis base? So a Lewis base, you can say, is any chemical species that donates an electron pair to another species. And we know that amines, they have a lone pair of electrons on the nitrogen atom. Okay, so this makes them good electron pair donors. Example, you can see ammonia, which is NH3. If you see primary amines like RNH2, R2NH, R2NH, which is a secondary amine, and R3N, which is a tertiary amine, so they all act as Lewis base. And if you see phosphine, which is PH3, it is also example of a Lewis base. Okay, so in this case we have nitrogen or phosphorus. They have these nitrogen or phosphorus atom. They has a lone pair that can be donated to form a bond with another atom or ion. Next, if they behave as a Bronsted-Lowry bases, then how can you define it? So a base is any substance that can accept a proton, okay, which is H plus ions. So when an amine, it reacts with water, it accepts a proton from the water molecule, okay. So this is the reaction which I was talking about. This is a primary amine. When it reacts with water, it forms an alkyl ammonium ion, which is RNH3+, and a hydroxide ion. Okay, so this reaction demonstrates that how amines, they increases the concentration of hydroxide ions in these solutions. Now, when amines react with, first see the thing that amines, they react with acids to form salts. This happens because amines can accept a proton from the acid, showing its basic character. Okay, so when it reacts with acid, it forms salts. Now these salts, which is formed from amines and acids, they are soluble in water, but they are insoluble in organic solvents. So the difference in the solubility is important if we consider purification and extraction process. So here if you see, when a primary amine reacts with the acid like a hydrochloric acid, it forms a salt. Here you will see it is alkyl ammonium chloride, which is RNH3+ and Cl-. Now these salts, they are soluble in water but insoluble in organic solvents. If we look at the specific example, here we have taken example of an primary amine, which is an aniline. Okay, in this nitrogen is bonded to two hydrogen and one carbon of this C6H5. So when this aniline reacts with hydrochloric acid, it forms anilinium chloride, which is C6H5NH3 plus Cl minus. Okay, so here this shows that amine group, it accepts a proton, and we will see this forms a resulting salt, and this salt is more soluble in water. If you'll see here, it is NH2. So this amine has accepted one proton. So if we see amine salts, when they are treated with bases like sodium hydroxide, we can generate the original amine. Now this happens because NaOH is a strong base and it removes the extra proton from the, if we say the example of a salt. Okay, so this removes an extra proton from the ammonium ion and converting back into the neutral amine. So if we see, if we have amine salt, which is RNH3 plus X minus, when we treat it with a strong base, then we can regenerate the primary amine. Okay, because you see that this strong base, it can remove this extra proton from here, which convert back into a neutral amine, which is RNH2. Okay, now if we measure the strength of a base, for that we use main two terms, the basicity constant, which is Kb, and its logarithm form, which is pKb. Okay, so these values, they help us to compare how strongly different amines can accept protons, which is what makes them basic. So if you see what happens in this reaction, when a primary amine reacts with water, it forms alkyl ammonium ion. Okay, so it accepts a proton from water and forms this alkyl ammonium ion and hydroxide ion. Now if we have to write the equilibrium constant, which is KEQ, so this is calculated by taking the concentration of products. Here what are the products? Alkyl ammonium ion and hydroxide ions. So we take the concentration of products and divide it by the concentration of reactants. What reactants we have here? We have primary amine and water. Okay, so this is how you write KEQ, which is equilibrium constant. Remember one thing, concentrations, they are usually measured in moles per liter. Okay, and if I specifically talk about what this equilibrium constant tells, so it tells us how far the reaction goes toward forming products. Now if here we are introducing a basicity constant, which is Kb. So Kb is equal to KEQ, which is equilibrium constant, into the concentration of water. Now since we know that water is present in large excess, so that is why its concentration is considered constant. Okay, so we will see that we will multiply with H2O on both sides. So I have multiplied KEQ with H2O, and here also I have multiplied it with H2O. So this H2O and this H2O gets cancelled out. And whenever we multiply two constant, here we are taking the concentration of water as constant. So when we multiply this constant into this constant, we get another constant. That is Kb, okay, which is basicity constant. So I can write Kb is equal to concentration of RNH3 plus into concentration of OH minus ions divided by concentration of RNH2. Okay, so this formula is important because it allows you to calculate the basicity of any amine if you know the concentration of these ions. Okay, now if we move forward, now as we know, the basicity of a compound is related to its ability to accept a proton. So we have seen the expression for Kb, So Kb equals the concentration of protonated amine times the concentration of hydroxide ion divided by the concentration of unprotonated amine. Okay, so Kb over here is a measure of how strongly the amine can act as a base. Higher will be the value of Kb, more the reaction favors the formation of base and hydroxide ion. Okay, so we often use pKb, which is the negative logarithm of Kb. Okay, so pKb is equal to minus log Kb. Now you need to remember a lower pKb values means a stronger base. If this value is less, we can say the base is stronger. Just like a lower pH means a stronger acid. So here see it is given up. A larger Kb indicates a larger Kb or a smaller pKb. Okay, a larger Kb or a smaller pKb indicates a stronger base. In other words, the more easily an amine accepts a proton, the stronger is its basic character. Okay, so remember this thing, larger Kb or smaller pKb indicates a stronger base. Now let us look at the examples. So here you see the table. Here you have pKb values for ammonia, methylamine and aniline. For ammonia, the pKb value is 4.75. For methylamine, it is 3.34. And for aniline, it is 9.13. Okay. So you can see this pKb values and you can comment that which one is a stronger base. So I told you a smaller pKb indicates a stronger base. So here methylamine has the lowest pKb value or has the smallest pKb value. That means methylamine is the strongest base. Okay. So if we see the basicity order, on the basis of pKb values, we can see methylamine is the strongest base. Then comes ammonia and the weakest one is aniline, because look at its value. The pKb value of aniline is too high. It is 9.13. Okay, so larger pKb values means a weaker base. So if we compare these three, we will see this is the strongest one and this is the weakest one. Now we are going to compare the basic character of alkyl amines versus ammonia. Okay, we will see that why alkyl amines, they behave as a stronger base than ammonia. Okay, so this is an important concept you need to pay attention. So first we know that alkyl amines, they are stronger base than ammonia. So this means alkyl amines, they are more likely to accept a proton in a chemical reaction. So first of all, the key reason is the electron releasing nature or positive inductive effect of the alkyl group, okay, which is often called plus I effect. So in alkyl amines, we know we have alkyl groups. So these alkyl groups, they pushes the electron density towards the nitrogen atom, which makes the nitrogen lone pair of electrons more available. So this increased electron density is what make alkyl amines a stronger base, because the nitrogen lone pair of electrons are more available in case of alkyl amines. So if you see over here a diagram that compares alkyl amines versus ammonia. Okay, so here you see you have alkyl amines where you have R group which is attached to this nitrogen, and this is ammonia. Okay, so see how the electron density around the nitrogen is higher in the case of alkyl amines. So when this accepts a proton, it forms this. And in this case, when this ammonia accepts a proton, here it is nitrogen which is bounded to 4 hydrogen atoms. Okay, and here this nitrogen is bound to 1 alkyl group and 3 hydrogen. So if you see over here this alkyl group or the electron releasing nature of this R group, this pushes the electron density towards nitrogen. And if you see in the case of ammonia, we don't have any R group. Okay. So if you see at this image, then you will clearly notice that alkyl amines, they are stronger bases than ammonia because of the electron releasing effect of the alkyl group. Another important point is that the substituted ammonium ion, which is formed when alkyl amine accept a proton, is more stable than the ammonium ion from ammonia. So I'm talking about this substituted ammonium ion. Okay, so this is more stable as compared to this ion, which is when ammonia accepts a proton and form an ammonium ion. So this increased stability, it also contributes to the higher basicity of alkyl amines. Okay, so if you see, I told you that this ion is more stable as compared to this one. This is because this stability comes from the dispersion of the positive charge by plus I effect of alkyl group. So if you see over here, this alkyl group, it spreads out the positive charge, which makes the ion more stable. Okay, so that is why this substituted ion, ammonium ion, is more stable as compared to this one. Okay. Now, if we're talking about the gaseous phase, okay, so in gaseous phase, the basic nature of aliphatic amines increases as we add more alkyl groups. This means that if we replace hydrogen atoms in ammonia with the alkyl groups like methyl or ethyl, the molecule becomes a stronger base. Now you know the reason. Why is this happening? Because alkyl group, they push electron density towards the nitrogen atom, which makes it easier for the amine to accept a proton. Now, if we look at the order of basicity in gas phase, okay, so this order will tell you that which type of amine is strongest base and which one is the weakest. So see over here, tertiary one is the strongest, then which is followed by secondary, then comes the primary, and then we have simple NH3. Okay. So if you see over here, students, look at the methyl groups. This is trimethylamine, which is a tertiary amine. This is more basic than this dimethylamine, which is a secondary amine, which in turn is more basic than this methylamine, which is a primary amine. And all of these three are more basic than this ammonia. So this trend is because of the increasing number of alkyl groups. Here you have 3 alkyl groups. Here you have 2 and here you have 1. Okay. So this is because of increasing number of alkyl group, which increases the electron density on nitrogen and make it a better proton acceptor. Okay. Now comes the main thing, that this trend doesn't always hold in aqueous state. Okay, that is, when amines are dissolved in water, their basicity order changes. This means that the presence of water and its interactions with amines affect how easily they accept proton. Okay, so if we talk about the basicity order in the aqueous phase, so in water, the basicity of amines, they basically depend upon 3 main factors. These factors are solvation effect, plus I effect, and steric hindrance. Each of these factors influences how easily amine can accept a proton. Okay, so don't get confused. This is the basicity order in gaseous phase. Now we are talking about basicity order in aqueous phase. And this is influenced by 3 factors. First is the solvation effect. So I give you an idea about this solvation effect. So this refers how well amine ion formed after accepting a proton can be stabilized by water molecules. So better will be the solvation, the more stable will be the ion, and stronger the base appears in water. For example, smaller ions, they are usually better solvated than larger and bulkier ones. Okay? Next effect is plus I effect or inductive effect. So alkyl groups, they pushes the electron density towards the nitrogen atom, which make it more basic. So that means more will be the number of alkyl groups attached, the stronger will be this effect. And the third factor which plays the role is steric hindrance. This means that bulky alkyl groups can physically block water molecules from surrounding and stabilizing the ion which is formed after protonation. So this can reduce the basicity of more substituted amines in water. So these are the three factors that affect the basicity in aqueous phase. So we are talking about the basicity in aqueous phase. First, we will discuss about solvation effect. I already gave you an idea about this effect. The solvation effect, which is also known as hydration. So when an amine accepts a proton, it forms a substituted ammonium ion. Okay? This ion is stabilized by hydrogen bonding with water molecules. So I can say more stable will be this ion, the stronger will be the base. Now notice that as the size of the ion increases, its ability to be stabilized by water through solvation decreases. In other words, I can say larger ions, they are less effectively surrounded and stabilized by water molecules, which make them less stable and therefore less basic. So if we look at this diagram, see over here the decreasing order of extent of hydrogen bonding, okay, and the stability of ions by solvation. Look here we have 3 hydrogens which are available for the hydrogen bonding. Here we have 2 hydrogens which are available for the hydrogen bonding. And here we have 1 hydrogen which is available for the hydrogen bonding. Now notice over here we have 1 alkyl group which is attached. Here we have 2 alkyl groups that are attached. And here we have 3 alkyl groups that are attached. So how water molecules surround and stabilize the ammonium ion, you have to pay attention. So this shows us that why smaller ions, they are better stabilized. Okay, so this is a smaller ion. So this is better stabilized. They can be more completely surrounded by the water molecules. Okay, so you will see this is the decreasing extent of hydrogen bonding and the stability of ions by solvation. Okay, so greater will be the size of the ion, lesser will be the solvation, and lesser will be the stability. Okay, so the key takeaway which you need to remember, the more stable the substituted ammonium ion, the stronger will be the basicity of the original amine. In other words, if I put this, I can say better solvation leads to a stronger base. Okay, so you need to remember this point. So if I summarize the basicity due to solvation effect, this is due to solvation effect. Then first is primary amines, which is more basic than secondary amines, and we have tertiary amines. Okay, so now you know why is this happening. This is because primary amines, they form smaller ions. Look over here, they form smaller ions which are better stabilized by the water. Okay, so this is the order because of the solvation effect. Now we were discussing about basicity in aqueous phase. Now we'll go to second effect, that is plus I effect. So another important factor that influences the basicity is plus I effect or electron donating effect of alkyl groups. So as we add more alkyl groups to nitrogen, they will push the electrons towards the nitrogen atom, which will make it easier for the nitrogen to accept a proton. So if I sum up, I can say the basicity increases as we increase the number of alkyl groups. So if we look at the basicity order due to plus I effect, then this will be the order. First is trimethylamine, which is a tertiary amine, which is more basic than dimethylamine, which is a secondary amine. This is more basic than a primary amine, okay, which is methylamine, and all of them are more basic than this ammonia, okay. So this shows as you are keep on adding the alkyl groups. Here there are 3 alkyl groups, here there are 2, here there are 1, okay. So as you are adding the alkyl groups, the basicity is increasing. Now we will see the third factor, which is the steric hindrance factor. Now steric hindrance, if we say, then greater will be the size of alkyl groups, greater will be the steric hindrance. Because bulky groups, they will hinder the approach of proton to the lone pair. Okay, so larger the alkyl group which is attached to the nitrogen, the greater will be the steric hindrance. This means that bulky groups, they can actually decrease the basicity even though they donate electrons. Okay, so over here you will see there is a balance between electron donation and physical crowding. So because bulky groups make it harder for the proton or H plus ion to approach the nitrogen lone pair. So more alkyl groups, they can increase the basicity through plus I effect. Too much bulk can actually reduce the basicity because of steric hindrance. Okay. So here we will see it was observed the order of basicity in water that doesn't follow a simple pattern. So this irregular trend happens because of 3 main factors: inductive effect, solvation, and steric hindrance. Okay, we have seen the order according to all the effect. We have seen according to inductive effect, we have seen according to solvation, and we have seen according to steric hindrance. So all of these factors, they contribute to the overall basicity order in aqueous phase. This is an irregular trend. I am again telling you, it is an irregular trend which is considering all these 3 factors. So first, if we are focusing on amines, where the nitrogen is attached to an ethyl group or a larger carbon, the number and size of these groups can change how easily the nitrogen can accept a proton. Okay, so this is for ethyl and more than 1 carbon substituted amine. Okay, so for ethyl or larger substituted amine, the basicity order is in aqueous phase. Okay, first is diethylamine, which is a secondary amine. This is more basic than triethylamine, which is a tertiary one, and this is more basic than ethylamine, which is a primary one, and all of them are more basic than ammonia. Okay, now this order might seem surprising, but this is due to the balance between the electron donating effect of ethyl groups and how well the resulting ions, they are stabilized by water molecules. Okay, so I will say you need to remember this order because it does not follow a regular trend. This is an irregular trend, and in exams it is asked very often. Okay, especially the basicity in aqueous phase, because this is an irregular trend. So I will emphasize that you need to remember this order. Now if we compare this to the amines with methyl groups that is attached to the nitrogen. So we know that methyl groups, they are smaller than ethyl groups. So the effect of solvation and steric hindrance, they will be different. So if you see for methyl substituted amines, the order is dimethylamine, which is the secondary, which is most basic, which is followed by methylamine, which is a primary, and then tertiary methylamine, which is a tertiary one, and finally we have ammonia. So this shows that the secondary amines are generally the strongest base, but the size and the number of alkyl groups, they can shift the order. Okay, so you need to remember that both type of alkyl groups and how well the ion is stabilized in water, this determines this basic strength. Okay, so I'm again telling you, you need to remember these order because they are a irregular trend, not a regular trend. Okay, so now we will see that aryl amines. Now we will compare between aryl amines versus ammonia. We have compared between alkyl amines and ammonia. Now we are going to see between aryl amines and ammonia. So aryl amines, they are much weaker bases than ammonia or alkyl amines. Okay, this means that they are less likely to accept a proton. Now, why this happens? One of the major reason is resonance and stability of anilinium ion. Okay, so in resonance, what happens? Electrons can be shared or spread out over several atoms. Okay, which makes the molecule more stable. So this stability affects how easily the nitrogen atom in aniline can accept a proton. So first let's talk reason 1, which is resonance. So resonance in aniline, it involves the lone pair of electrons on the nitrogen atom. Now this lone pair doesn't just stay on nitrogen, but it interacts with the benzene ring. So you will see over here that the lone pair on nitrogen in aniline, it is delocalized or it is spread out into the benzene ring. This means the electrons, they are not just sitting on nitrogen, they are shared with the ring. So because this lone pair is delocalized, it is less available for protonation. In other words, nitrogen can't easily grab a proton, which makes aniline a weaker base compared to ammonia, which in ammonia where the lone pair is fully available. Okay, so look over here the resonating structures of aniline. Okay, so you will see over here that the lone pair on this nitrogen, it is delocalized into the benzene ring. It is not localized. Okay, so this lone pair is less available, and that is what makes aniline a weaker base. Okay, so you will see over here this lone pair is spread out into the whole ring. Okay, it is just not localized on the nitrogen. This is the main reason why aniline is a weaker base. Okay, reason 2 comes the stability of anilinium ion, which forms when aniline accepts a proton. Okay, so when aniline accepts a proton, it forms a anilinium ion. This means a hydrogen ion or a H plus ion, it attaches to the nitrogen atom in aniline. So the resulting ion is positively charged and it is called the anilinium ion. So if you see over here, aniline, which is C6H5NH2, okay, it reacts with H plus to form the anilinium ion. So this has accepted one proton and formed an anilinium ion. So see, this nitrogen gains an extra hydrogen and carries a positive charge. Now the anilinium ion has two different resonating structures. Okay, now focus on the thing that fewer are the resonating structures, that means less is the stability. So if you see, these are the resonating structures of anilinium ion. Okay, so see over here we have limited resonance. So this limited resonance is a key reason why anilinium ion is less stable. Okay, here you will see they have only two resonating structures. Now in general we know more the resonating structures a molecule has, the more stable it is. This is because the charge and energy, they are spread out over more arrangement, which makes the molecule less reactive, okay, and I can say more comfortable in its state. So now we know that aniline has 5 resonating structures, while the anilinium ion, it has only 2. This means aniline is much more stable than its protonated form. Okay, the difference in the number of resonating structures explains why aniline is a weaker base compared to ammonia. Okay, so if we see the basicity order, then we know that ammonia is more basic than aryl amines. Okay, this is because ammonia forms a more stable ion after accepting a proton, while aniline's ion, which is anilinium ion, is less stable because it has fewer resonating structures. Okay, so I hope now it is clear between alkyl amine versus ammonia and aryl amine versus ammonia. Okay, I have told you the reasons for both. Now we are going to talk about the effect of substituents on aniline. Okay, so the substituents that are attached to the benzene ring in aniline, they can change how basic the amine is. First, if we talk about electron donating groups like OCH3 group or CH3 group. So these group, they push electron towards the benzene ring and the nitrogen atom. So this extra electron density makes it easier for a nitrogen to accept a proton, which in turn increases its basicity. Okay, so we know that the electron donating groups, they increase the basicity through plus R effect or plus I effect. This means that they can share electrons through resonance or push electrons through the sigma bonds, both of which make amines more basic. Okay, so if I give you an example, if you're adding a methyl group, that is a CH3 group, to aniline, it will make it a stronger base. Now, if on the other side, if we talk about electron withdrawing groups like NO2, SO3H or COOH, okay, and if we talk about halogens, then what they do, they pull the electrons away from the benzene ring and the nitrogen atom, okay. This reduces the electron density on nitrogen, which makes it less able to accept a proton and thus decrease its basicity. Okay, so as I told you, the same reason, this decreases the basicity through minus R or plus I effect. Okay, for example, if you add a nitro group to aniline, its basicity will drop significantly. Okay, so look at this basicity order. If you see, we will see para-toluene, in which a CH3 group is attached to aniline, is most basic. Then comes a simple aniline, and then comes this para-nitroaniline, where our electron withdrawing group is attached to aniline. Okay, so now you know the reason. If you have electron donating groups, they increase the basicity through plus R or plus I effect. And if you have an electron withdrawing group, it decreases the basicity through minus R or minus I effect. Now, if we focus on alkyl amines, then alkyl amines are more basic than ammonia. Okay, this is because alkyl group, they push electron density towards nitrogen atom by inductive effect. So this extra electron density make it easier for the nitrogen to accept a proton and increase its basicity. If we see about aryl amines, then aryl amines, they are less basic than ammonia or alkyl amines. Okay, this is because in case of aryl amines, they are less basic is due to the resonance. The lone pair of electrons on nitrogen atom, they can delocalize into the benzene ring through resonance. So this means the nitrogen lone pair, it is less available to accept a proton, which reduces the basicity of aryl amines compared to alkyl ones and ammonia. Okay, so overall basicity order is alkyl amines, which is more basic than ammonia, and ammonia is more basic than aryl amines. Okay, so this is the overall order which you need to remember. Okay, we have discussed each one of them in very much detail. So I hope now this basicity order is very much clear to you. Now there is one question in which you have to arrange the following in decreasing order of the basic strength. Okay, so if you see over here you have ethyl amine, you have aniline, you have ammonia, and you have diethylamine. So I hope now it is clear how to arrange it. So if we see over here, then we can see on the we can focus on the effect of alkyl groups, which is called the inductive effect or plus-I effect. Okay, so alkyl groups, they if we talk about ethyl, then they push the electron density towards nitrogen atom, which makes it easier for nitrogen to accept a proton. Okay, so if we talk among ammonia, ethylamine and diethylamine, more alkyl groups which is attached to nitrogen, the stronger will be the base. Okay, so if you see over here, then in diethylamine, this is most basic, which is followed by ethylamine and then ammonia. Okay, because you will see in this case, we have two alkyl groups which is attached. Okay, so because of this increasing alkyl groups, this will increase the electron density on nitrogen, which will make it a better proton acceptor. Now if we talk about aniline, so the lone pairs on nitrogen is involved in resonance with the benzene ring, which is making it less available to accept a proton. Okay, so this will make aniline less basic than ammonia. Okay, so if you see over here, you will see that aniline is less basic than ammonia because its lone pair on nitrogen is delocalized, which is reducing its ability to accept a proton. So if you'll see the decreasing order of basic strength, first you will see we have diethylamine, which is followed by ethylamine, we have ammonia, and then we have aniline. Okay, we already discussed in the case of arylamines versus ammonia versus alkylamines. Okay, so this is the decreasing order of basic strength. Now we will talk about alkylation, which is another type of reaction. So here we see that amines, it reacts with alkyl halides to produce a mixture of amines. And this happens through a nucleophilic substitution reaction. So if you see over here a nucleophile, okay, which means the amines, they will act as an electron pair donor, which will attack another molecule to form a new bond. So if we see the nitrogen atom in amine, they have a lone pair of electron which makes it reactive. So this lone pair is what allows the amine to attack other molecules, especially the carbon atom in alkyl halide. Okay. So the lone pair on nitrogen, they target the electrophilic carbon in alkyl halide. Okay. So because this carbon is electron deficient, okay, because it is attached to a more electronegative atom, okay, like a chlorine or a bromine. Okay, so this sets up the condition for a nucleophile to attack and a nucleophilic substitution to occur. So if you look at this, here we have a primary amine. When this primary amine reacts with a molecule of alkyl halide, we have a secondary amine. And this secondary amine, when further reacts with another molecule of alkyl halide, we have a tertiary amine, which further reacts with another molecule of alkyl halide, and we have a quaternary ammonium salt. So if we look at the specific example, here you will see you have ethane amine, which reacts with methyl chloride to form N-methyl ethane amine. Okay, so I hope now you know this nomenclature, that this methyl is directly attached to this nitrogen. So this is N-methyl, and this is the parent chain. So this is ethane, and E of ethane is replaced by amine. So it is ethane amine. Okay, so if you see over here, this carbon is electrophilic in nature. So this nitrogen will attack this carbon over here and eliminates this Cl from here. Now this N-methyl amine will react with another methyl chloride and form N, dimethyl ethanoamine. And this will react with another molecule of methyl chloride and will give you a ethyl. It will give you ethyl trimethyl ammonium chloride. Okay. Now notice that both primary and secondary amines, they can react with acid chlorides, anhydrides and esters. Okay. This reaction forms amide through a process which is called nucleophilic substitution reaction. Okay. So here we are specifically talking about the acylation. Okay. So here you will see a nucleophile which can donate its pairs of electron, will form a new bond, and the amine, it will act as a nucleophile here. Okay, so this is what is happening in acylation. Now the reason acylation happens is because primary and secondary amines, they have replaceable hydrogen atoms which is attached to nitrogen. And these hydrogens, they can be substituted during the reaction, allowing the acyl group to attach and form the amide. Okay. Now this distinguish between primary, secondary from tertiary amines. We know in tertiary amines we lack this replaceable hydrogen. So this replaceable hydrogen is only present in primary and secondary amines. So for this reaction to proceed efficiently, we need a base that is stronger than amine. Okay, so the base will help neutralize any acid that is formed during the reaction. So you will see a good example of a stronger base which we use here is pyridine. So pyridine acts by removing the hydrochloric acid that forms as a byproduct during the reaction. So by doing this, it prevents the buildup of acid which could otherwise react with ammonia, and it could reduce the yield of desired amide. Now by removing the HCl, the bases like pyridine, they help shift the equilibrium of the reaction to the right, meaning more product is formed. So the application which is used over here is a very famous application which is Le-Chatelier's principle, and it states that a system will adjust to minimize the change. Okay, so in this case, if we are removing a product that is HCl, it drives the reaction forward. So if we look at this specific example where we'll talk about acylation reaction of primary amine. Okay, so here you will see you have ethane amine, which is a primary amine. It reacts with ethanol chloride. Okay, in the presence of a base which is pyridine, and it produces N-ethyl ethanamide. Okay, and hydrochloric acid. So you will see over here this hydrogen of amine, it is replaced by this acyl group which is C double bond O CH3. Okay, forming this amide and a byproduct which is hydrochloric acid. Now if we see the mechanism of this reaction, then you will see what happens in this reaction. The nitrogen which has a lone pair in ethene amine, it will react this electrophilic carbonyl carbon of ethynyl chloride. Okay, and you will see you will get this complex, and further what happens, this chloride will eliminate from here and you will get N-ethyl ethanamide. Okay, so the amine attacks the carbonyl carbon of acid chloride, which leads to the formation of this amide and the release of HCl. Okay, so this is the mechanism of this reaction. Now we were continuing with the acylation. Now we are going to see acylation reaction of 2-degree amines or secondary amines. So if you look over here with the chemical reaction, here you have N-ethyl ethanamine, which is a secondary amine. When it reacts with acetic anhydride, it forms N, diethyl ethanamide and acetic acid. So you will see over here this replaceable hydrogen of a secondary amine. Okay, it gets replaced by this acyl group over here, and it also forms an acetic acid. Okay, if we look at the mechanism of this reaction, so we will look this step one by one. Okay, so if you'll see over here, then this nitrogen which has a lone pair will attack on this carbon of acetic anhydride. Okay, which will form this complex, and further what will happen, this oxygen which has a negative charge will form a carbon double bond oxygen, and this group will leave from here. Okay, which further forms acetic acid, and you have N, diethyl ethanamide. Okay, so this is what is happening in this reaction. Now if I talk about tertiary amines, I told you in tertiary amines you don't have any replaceable hydrogen. So in case of tertiary amines, they do not undergo acylation. Okay. So if you see here, you have triethylamine, which is a tertiary amine. When you react with acyl chloride like ethanol chloride, it will give you no reaction. Because see over here, you have no hydrogen that will get replaced by this group, by the acyl group. So that is why no reaction will take place. Now we will specifically talk about the Schotten-Bowman reaction. Okay, so what happens in this reaction? A amine reacts with benzoyl chloride, which is C6H5COCl. So amine over here acts as a nucleophile and it attacks the carbonyl carbon of benzoyl chloride, which leads to the formation of a new compound. So if we look at this Schotten-Bowman reaction, we have methane amine. Okay, it reacts with benzoyl chloride and it forms N-methyl benzoamide and hydrogen chloride. Okay, so you can see over here that the amine group from this methane amine, it combines with the acyl group from this benzoyl chloride to give this particular amide over here. Okay, so this we got an amide. This is a Schotten-Bowman reaction. Now if we look at the mechanism of this reaction, what happens in first step? In first step, the lone pair of electrons on nitrogen, they act as a nucleophile. Okay, so in this case, the nitrogen is attracted to a positively charged or electron deficient center. So lone pair will act as a nucleophile. Now this nucleophile will attack on the electrophilic carbon in benzoyl chloride. Okay, so this carbonyl carbon is electrophilic because it is partially positive, because it is double bonded with oxygen, which is pulling its electron density. Next, after the attack, we will form a tetrahedral intermediate. This means that the carbon, which was previously double bonded to oxygen, now has 4 single bonds, which is giving it a pyramid-like structure. Okay. Last step, this tetrahedral intermediate will finally collapse and it will rearrange to become more stable. So this chloride ion during this process will be removed and get the final product, which is N-methyl benzoamide. Okay, so this is the whole mechanism as I have told you. Okay, so first is this lone pair of nitrogen. This lone pair of nitrogen over here will attack this carbonyl carbon, which is electrophilic. Okay, this will form this tetrahedral intermediate and the chlorine will eventually leave, and this tetrahedral intermediate will finally collapse to give you N-methyl benzoamide. Okay, so this is the mechanism. Now we will talk about fourth one, which is carbyl amine reaction. Okay, so this reaction is used to identify primary amines. Okay, so this test, it will work for both, which is aliphatic and aromatic primary amines. Okay, now what happens in this reaction? Primary amines, they are heated with chloroform, which is CHCl3 and ethanolic KOH, which gives you isocyanide. Isocyanide where nitrogen is triple bonded with carbon. Now these isocyanides, that is the product of this reaction, they are known for being highly toxic and having a very false smell. Okay. Now it is one important thing to note that only primary amines give a positive carbyl amine test. If you try this reaction with the secondary or tertiary amines, you won't get the same result. Okay, so this test is a reliable way to distinguish primary amines from other types. So if you look at this reaction of primary amine, it reacts with chloroform and 3 molecules of potassium hydroxide. When it is heated, it gives you isocyanide, 3 molecules of potassium chloride and 3 molecules of water. Okay, so if you see over here, if you increase the amount of primary amine, you will get more isocyanide. Okay, as long as you have enough of the other reactants. Now secondary and tertiary amines do not give this test. Okay, that's because they lack the necessary hydrogen atoms on the nitrogen atom, okay, which are required to form this unstable isocyanide intermediate. Okay, so the reason is given same, because you will see there is absence of necessary hydrogen atoms on the nitrogen to form unstable isocyanide intermediate. Now we will next study the reaction of nitrous acid, which is HNO2. So we'll see the preparation of nitrous acid. So to make nitrous acid in lab, we react a mineral acid like hydrochloric acid with sodium nitrite, okay, which is NaNO2. So this reaction happens just before we need the nitrous acid, okay, because it breaks down quickly if it is left standing, okay. So this is unstable acid which is prepared in situ. So if you see sodium nitrate, when it is reacted with hydrogen chloride, it gives you nitrous acid and sodium chloride. Now we will see the reaction of nitrous acid with primary aliphatic amines, okay. So when a primary aliphatic amines, it reacts with nitrous acid, it forms an unstable compound which is called aliphatic diazonium salt. So this intermediate doesn't last long, especially at room temperature, and it quickly breaks down. And this unstable diazonium salt, it then decomposes, producing an alcohol, nitrogen gas, and hydrochloric acid. Okay, so the nitrogen gas is released as bubbles, which is a visible sign of this reaction. So if you see here, we have primary aliphatic amines. When you react with nitrous acid at 273 to 278 Kelvin, you get an alkyl diazonium chloride, okay, which is unstable aliphatic diazonium salt. It further decomposes to give you an alcohol, nitrogen gas, and hydrochloric acid. So this is the reaction of HNO2 with primary aliphatic amines, where you need to remember the products. Now we will see reaction of HNO2 with primary aromatic amines, okay. So this process is specifically called diazotization. So what happens in this reaction? It needs to be carried out at low temperature, specifically between 273 to 278 Kelvin, which is 0 to 5 degrees Celsius. At these temperatures, the primary aromatic amines, they react with cold nitrous acid to form a stable diazonium salt. So see over here the chemical reaction. Here you have aromatic primary amine which reacts with nitrous acid and HCl at a temperature 273 to 278 Kelvin, and you get a aromatic diazonium chloride along with water, okay. Now aromatic diazonium salts like the one which is formed here, they are much more stable than aliphatic diazonium salts, okay. Now this is the reason for this increased stability is because of the extended resonance in the aromatic ring. So the positive charge on the nitrogen, they can be delocalized over the aromatic system, which spreads out the charge and stabilizes the molecule. Okay, so this is a resonance stabilized aromatic diazonium salt. Okay, so we'll see over here the positive charge on the nitrogen, it can be delocalized over the aromatic ring, which is spreading out the charge and stabilizing the molecule. Okay. Now we will see the reaction of nitrous acid with secondary amines. Now secondary amines, they react with nitrous acid to form a yellow oily liquid which is called N-nitrosoamine. Okay, so this is a characteristic reaction and it helps you to identify secondary amine. So if you look at this reaction, you have diethylamine, which is a secondary amine. When it reacts with nitrous acid, you get N-nitro, so diethylamine, okay, which is a yellow oily liquid, and you get H2O. Now if we see about the reaction of HNO2 with tertiary aliphatic amines, okay, so they react with nitrous acid and they form soluble nitrite salts. So if you see tertiary amines, when it reacts with nitrous acid, it will give you tertiary ammonium nitrite salt. Okay, So over here you will see that the nitrogen atoms in the amine, they gain a hydrogen and a positive charge. Okay, while the nitrite ion, which is NO2 minus, this balances the charge. Okay, so this is the reaction with tertiary aliphatic amines. Now if we see the reaction with tertiary aromatic amines, then this undergo electrophilic substitution at the para position. Okay, so what happens in this reaction? The electron rich part of the molecule, like the aromatic ring, it is attacked by an electron poor species, like an electrophile. Okay, so as a result of this reaction, we get para-nitroso compound. Okay, which indicates us that the NO group, which is attached to the para position. So these compounds, they are often green in color, which helps you to identify in lab. So look at this particular reaction. Here you have a tertiary aromatic amine, which is NN dimethylaniline. When you react with HNO2 at 273 Kelvin in presence of NaNO2 and concentrated HCl, you get a para-nitroso NN dimethylaniline. You will see this NO group get attached at the para position to this group. Okay, so this is the reaction with tertiary aromatic amine. Okay, thank you so much students for your attention. I hope the lesson which we discussed today was helpful to you. Thank you so much.